And the reason that conditional probability is so important now is because it leads us to what we call independence. And independence is a very powerful concept in probability. And it says this: two events are independent if the occurrence of one event does not affect the occurrence of other event. If it rains today, it will have no effect on it raining tomorrow. If I flip a head with my coin, it has no effect if you flipping a head with your coin. Those events are independent of each other. All right? So if those events are independent, then we can always assume that things are independent. We can always assume that they're independent. And when we assume that, what we're really doing is, if two events are independent, we assume they're independent, we're going to develop what's called the multiplication rule. And the multiplication rule just says this: the word independence in probability literally means to multiply. So if two events, and look right here, it says if two events occur in sequence, that means if I flip a coin and you flip a coin, or if it rains today and it rains tomorrow. When I use that word and, I'm using a sequence, and I'm saying that the probability of event A and B occurred. That's what I'm really saying when I say the word and. And if those two events are independent, the probability is just equal to A times the probability of B. And what this really means then is that anytime we see the word independent, we can just multiply the probabilities. And those when you multiply those probabilities, they will give us, remember this right here, this part right here is called the intersection. So it gives me the and part of it. All right? And I'm assuming this right now. I'm assuming independence. Well, this assumption will lead us to what we call the mathematical independence. And here's how we show that two things are independent mathematically. We can use the conditional probability, because the conditional probability says that if one event already occurs, what's the probability of the other event? Well, if the two events are independent, regardless if one event occurs, it shouldn't affect the occurrence of another event. So we use the definition of the condition. Here's what we get: the probability of B given A. So the probability of B given that A has already occurred was equal to this right here: the probability of A and B divided by the probability of A. Remember, we restricted the sample to this, and it's the intersection at the top. But if the two events are independent, or we assume independence, then this is what should be true right here: the probability of A and B should actually be equal to the probability of A times B. So look what we have sitting up here. We have A and B. So we can rewrite this as the probability of A times the probability of B. All that divided by the probability of A. And notice that you have probability A on top and bottom, so they cancel out. So if two events are truly independent, because we assumed independence right here to get here, but if they truly are independent, then what this says is that the condition is equal to the probability of just B here. So when I write this, the formal definition of independence is the probability of B given A is equal to the probability of just B. So now we're going to actually show independence, or try to check to see if things are independent mathematically using that formula. And we're going to use the one we just did. If a man's height is independent of his income earnings? In order to do this, you need two events. In this particular case, I have height and income earnings. I can pick either one I want to. I can either pick short men, short broke men, or short rich men, or tall rich men, or tall broke men. I'm going to use the one I already have, which was this probability right here. You always start off by finding a condition between the two events. So I'm going to find the probability of a man. Remember, we restricted it to a man being tall. He was a high income earner. And that was equal to 101 out of 123. Then we get a decimal for that. I get a value of 0.821. That's the first part. Find a conditional probability between the two events. You can pick any event you want to. I could have done tall first and high income earner second. It would have changed the values, but you would have got something like this. And the reason it doesn't matter is because if the events are truly independent, whether you do tall or high, tall income earner first, tall person, high income earner first, or high income earner, then tall person, either way it goes, in the end, they're going to show that you're independent. And so the next part is find the probability of the back event. And this should actually be find the probability of the front event. Because we're going to use the definition now. And remember what the definition says. Find the condition first. We found the condition. That means that we need to find the probability of the front event, which is the probability of H. Well, I want to find the probability of H. That's high income earners in the sample. There are 149 high income earners in the sample out of 192 total. So again, we're going to find that decimal. That's equal to 0.776. Now here's how you tell if they're independent or not. If I know the condition and I know the front probability, which is also called the marginal probability, if I know their probability there, I can compare them. If they are truly independent, these two values should be the exact same thing, because that tells me that one thing, that your height does not affect your income. So when I look at this and I compare it, I have 0.821. Does that equal 0.776? The answer here is no, they're not equal. And because they are not equal, no, they are dependent. If they were equal, we could say that it was independent. But because they are not equal, we are telling you that no, they are dependent. In this case, typically in this sample, it looks like more men that are tall tend to be the high income earners as well.